So maybe let's take this opportunity to thank Bernardo, the organizer. Didn't want Bernardo to. We have Bernardo speaking on behalf of Dev Sinha.
So thank you for staying until this time. Let me quickly explain what happened. I invited, well, a lot of people accepted, some of you couldn't come. Dev Sinha has a problem. His daughter is sick, and so he cannot leave home at all. But he wanted to share some ideas and thoughts about bordism, and so we talked on Zoom because he asked me, could I give an online talk, and I refused. Sorry, I said no, it's completely in person. But then we met on Zoom, and he told me, well, let me tell you what I was going to say. And so I told him, well, I can give a talk on your behalf. And he said, oh, great, let's do that. So we talked on Zoom. He explained to me, didn't understand what he was saying. It took me a week to study. So I felt again like in grad school, I had to study papers. But then he told me, look, I will not be able to organize a talk for you to give. I have no time. So let's talk again. And you, Bernardo, present something. You present what you think is presentable. So the third time we met last week, so he wrote these 3 pages ideas. And when I saw the 3 pages ideas, of course they have no context. They start the first line and talk about my paper, page 32. So I felt I need to contextualize this. So the first page, he is wanting to say to this group of people that in a paper he published in 2001, which is being quoted as one calculation for equivariant bordism rings, and there was some mistake in some assumption that he made that he was not careful to check that. Bernhard Hanke present read the paper very carefully, I suppose, and found something that was not somehow correct on one assumption. And this assumption that he used derailed some proofs. Not everything is wrong with the paper, it's just derailed the proof because he could not do a filtration that he was doing, and then some completeness of array could not be used. But nevertheless, Dev thinks that there's something there to be shared, and this is what I'm going to do. So I want to share his thoughts through me. So of course it will come awkward because so you have all of you have this, so you might read it. On the first page, he states what's the problem on his proof, and then on the second and third page, he wants to somehow bring some problems or some ideas or some thoughts about it. So I'm not going to focus on this paper because you have it, but the paper he's talking about is called Computation of Complex Equivariant Bordism Rings, published in 2002. This was somehow the outcome of his PhD thesis. Ernesto was in the Stanford when you were a student at the same time, no? So talking a lot about his thesis. So Dev was a student of Gunnar Carlson, and so he published his results when he was already working, say. So let me just perhaps go to the theorem, 5 point something, on which he uses a lot of the constructions that are there in the air. Let me see, where is it? Here. This is the statement that I want to point out. So how do I move this? So the point is that we want to give some sort of generators and relations on the equivariant bordism, homotopical equivariant bordism ring when T is this circle. T is the circle here all the time. It's just a circle, but it's not very difficult to circle. And so what he claims is, or what he wanted to claim, that perhaps I just call it now conjecture, is that if you take some Euler classes of representations, irreducible representations, and certain classes that are precisely measuring fixed point data or the specific generators of the bordism ring, this is the EV class, and this is the projectivizations of a representation with a trivial one. with some specific constructions, maps that he call it gamma, which is a composition of some classes that I will explain. What he wanted to claim is that these two classes plus these functions generate all the elements in the equivariant Bordism ring. And he wrote a set of relations that these operations do have, but the proof is based on some specific properties that these gamma functions have that they're not correct. And so I will show you what is not correct, but then we learn a little bit among the things that he was saying. So let me just, after telling you what is the point of the talk, so let me just start, and I will start from zero. The derivative will be high, but I'll start from zero. So, zero, no? So what are we talking about? This is the equivariant version, but I believe if you have the geometrical version in your head, if the homotopical one is too abstract, then keep the geometrical version in your head. And the homotopical one has different properties. So we want to take manifolds with an extra structure that is an almost complex structure in the stabilization. So you take a manifold, take some copies of the reals, and add it in. If you can add an almost complex structure on this bundle, then we call this manifold unitary unitary or stable with a stable complex structure. And what we want to do is we want to mod out the relation which is being coordinate, as in the picture that we know, being coordinate, no? It's a picture. Of course, it says nothing, but it's just a picture. So if I have a manifold here, a manifold there, change the orientation, and if you can fill it with another one, then they are in the same equivalence class. We can do this for every dimension. So we have, and we did this union, we make this set into a group, and then we can put them all together for every dimension, and then we have a graded group. And this graded group, of course, you should think of it, well, I think of it as telling me which are the generators of the, or which, when two manifolds with an action are coordinate. This is how I think of it. If you put your manifold and you send it there and it becomes zero, then it's coordinate. This is how I think of it. But it's moreover a ring, because of course you can just take two manifolds and do the cross product of the manifolds and take the diagonal action. Really nice. And it's also a module over the non-equivariant Bordism group. Take a manifold with an action, one without an action, with a product, they become a one with an action. But there is a homotopical version of this gadget, which is you have to, as Mona was saying, if you do it this way, there is some problem. There is a lot of problem because you cannot dualize. There are many difficulties. You cannot do transversal intersection. And one way out is to smooth all those things by stabilizing the structure. And this is, it was done firstly by Tom Dick. Bernard should correct me, but it was Tom Dick, the one who did this homotopical version of equivariant Bordism, which is simply by using the Tom-Tragen-Tom construction, simply there is the geometrical version of the Bordism and there's the homotopical one using the Tom spectrum, which is simply by taking the universal principal bundle with UN actions, this one, the associate one, and then you just do the Tom construction, namely you take the sphere bundle, the ball bundle, and then collapse the sphere on a point, and you produce some limit, and the homotopy groups, the stable homotopy groups of these things, become, by a very famous theorem of Tom, they become the Bordisms groups. These are the geometrical ones, and these are the homotopical ones. Whenever there is no group action, they are the same. So for you to know, so this ring in the non-equivariant case is a polynomial algebra on one generator in each even dimension. There are explicit generators for these objects, which are the Milnor hypersurfaces, and also there are other type of construction done by Buchstaber and Ray, which are toric manifolds of a specific kind. But whenever you tensor with the rationals, it's just a polynomial algebra on the projective spaces. Of course, you can put a G on all these pictures, and then you have a geometrical version of these gadgets, which is these equivariant bordism groups. And they somehow come from works of Attila, Conrad Floyd specifically, and Stone. So what you should think of it is, again, these are manifolds with an action, with an appropriate, stably, almost complex structure living on X. And in this case, there's also a homotopical version after Tom Dick, which is we just again construct the universal principle, well, a universal vector bundle with a G action. This is my B sub G U K. Namely, you take all possible representations, take infinite but of dimension K if you want, and then you take the Grassmannian, and this is it. But then you need to, you do it properly, you stabilize this picture by just simply adding all possible representations. And when you do this stable version, as Mona was saying, then we just get a spectrum, a equivariant spectrum, and the homotopy groups of these objects will be the equivariant homotopy unitary groups. The thing is that we can, of course, do the total tracking map, take a manifold, embed it into some big representation, take the normal bond, collapse it to a point, but the same construction as the some map, and then you get a map from the geometrical one to the homotopy. If you take the G out, it's an isomorphism. But if you put the G, it's a homomorphism for the time being. We don't know exactly many somehow properties of it, but we know for specific groups. And what among the new things that appear on the right-hand side that are not on the left-hand side are these Euler classes of the irreducible representations, whose without somehow interesting fixed points. And one way to imagine this thing that I was somehow, this is an idea of that he was teaching me, is that one can get this representation and one can take the ball of the representation and the sphere of the representation as a pair, and you can just send this point to 0, and of course this somehow will amount to some element on the bordism, the 0 of BB SB, and if the representation has this property on which the only fixed points are the 0, then they represent an element which is non-trivial. So this point here represents some element in here. But the point is that there is a very nice way to stabilize the geometrical bordism groups. And one way to stabilize it is to simply construct all these things for all the possible representations, and then these will give elements in the equivariant bordism ring of a point. Yeah, exactly. So if we somehow could do this some construction all over the representation, and we take the limit, then this element that I just constructed defines precisely an element here. So locally, you can just think of a point on this representation, in this sphere bundle, but you can just put all others and then you get a specific element. This is this Euler class in here that of course will not exist on the geometrical one. The geometrical is all positive dimensions and this is negative dimension. So one question is, of course, depending on your taste. My taste is that I want to know the left-hand side, some other people want to know the right-hand side. Doesn't matter, let's find both. But the idea is what can I learn from the left-hand side, from the right-hand side, or vice versa, or what can I say from each one, which is precisely understanding what is the information on these rings. And so the question is not trivial to answer. What are these coefficients for every single group? Some things are known. So let's start with the simplest question, what is the structure as a module over the bordism ring that is not equivariant? And nice things were proved on it, especially if you have a compact abelian group, then the equivariant bordism ring is a free module of the other one on even dimension generators. And And somehow, I'm sure Igor knew this many years ago. And there was the question of this is the case for every group, whether the equivariant bordism ring is a free module on the bordism ring that is non-equivariant on even dimensional generators. But somehow,
By the way, what Lazaret? What Lazaret?
Lazaret. Wow, sorry. It's Lazaret and not Lazarov. And by thinking about this problem, Eric and collaborators of mine, we by some work that did Eric that we saw, we found that by calculating explicitly the second group of the equivariant bordism ring, we found some torsion elements, very explicit torsion elements. We explicitly calculated this object, and we got a very nice element that existed before, which is the Bogomolov multiplier, and we got a lot of Bogomolov multipliers in these bordism groups. Namely, there are torsion elements. They appear in dimension 2. Still, we don't know what happens in dimension 3 nor dimension 4. We're thinking about it, Eric, more than me. But more or less at the same time, Sophie here present very nicely also found that this freeness of the homotopical equivariant bordism ring was false by doing a very nice calculation by bringing some construction that had done Igor in the 2001 or 1999, where he somehow showed that some conjecture of Hopkins, Kuhn, and Ravenel on Moravec theory was false. The conjecture of theirs was the Moravec theory of the classifying space of finite group should only land in even degrees and be free. So Igor got a group, the still of subgroup of this GL4 FP, and with a specific, very nice argument of a spectral sequence, he showed that there was some torsion element. And Sophie very smartly brought this construction all the way back to the homotopy bordism ring from the Moravec theory, but there, and she showed that this class survived, and therefore there was also torsion classes in this one. So interestingly, so they are not related.
So just like a small point, what my result releases that these coefficients are not flat or they're not even. So we don't know.
Okay, so I misunderstood. Somehow I thought that I could. But hey, so maybe so let's say what she. Let's not read what I wrote. These are my words. What she says that they are not flat as a MUG model.
Or they're not flat generated, or not flat, or they're not generated.
They're not flat. Minor. So she disproved also the same somehow statement in this case for these groups. But that's not the point of the lecture. So the idea was now. So what is the equivalent bordism ring for different groups? It's very difficult. It's very difficult to calculate. So I just put some names here, and if some name is missing, please let me know. In 2001, Strickland explicitly calculated the generators and relations for this equivalent bordism ring for Z2. I put on the bottom, to me it's very complicated. To understand these relations and group and generators is very complicated. That doesn't mean that it's not correct, it's just very complicated.
So there are some more developments. So with Abraham, we did it for every finite abelian group, but that's not so important. But now also we have this new work with Yinze Blue, and that has an explicit generators and defining relations, which are basically actually just, I mean, they're simple, they're not so usable, but for the primary cyclic also Poku has very explicit generators and relations, and those are actually good enough to actually construct examples of complex oriented spectra. Yeah, there's
Sorry.
new developments.
Again, I was doing this on a run, so I apologize if things are. I said all this, but this talk is awkward. So, Dev was for this around the time calculating the thing for the circle. Igor had a very nice construction for the cyclic subgroup CP. Oh, don't know exactly. The point is that recently also Bernhard and Wimmeler showed explicitly the relation between the Lazar's equivariant formal group law, the universal formal group law, with this equivariant bordism, generalizing a theorem Quillen, and more recently, Hausmann proved it for all abelian groups using this global equivariant homotopy theorem.
All of these are homotopy.
Yeah, this is all homotopy. Yeah, yes, it's all homotopy. Yeah. So I asked Bernhard about if one can recover if you put here A the circle, if one can recover the whole information that Dev wanted out of this theorem of Hausmann. That Bernhard says that yes. I said yes because he said yes. So I'm doing yes.
Maybe I make one remark on the left-hand side. This equivariant Lazarin. Okay, so this goes back to a definition of Paul Greenlees and Fritz, who defined what a G equivariant formal group law is. You have a number of axioms, it's an algebraic object, and this Lazarin is the universal object. And so we have generators and relations. Absolutely.
Somehow.
Okay, so that's it. And then, so now the question is, can one interpret these generators and relations in a sort of semi-geometric sense?
Yeah, good point.
I think
Exactly.
that's how it's
So if I can still comment, so
Yes.
actually one of our co-authors also was Mike Paul, so with Greenlees on the definition of equivariant form. So Mike Paul, it was in fact his thesis where he did the first, well, we also defined it a little bit.
And I said this, maybe you can just didn't hear it. Cold green is
Yeah, oh, sorry.
Greenlees and yeah, of course. You have something to say?
Also, Jack Carlisle recently calculated the omegas in multiple stars.
Omega thing.
So that the geometry.
Nice. You see, I'm glad I'm talking, so now I get all the information flowing to me. But again, I apologize for all this missteps. So there are many, of course, tools to play, but there are at least two very known and important. One is to localize on fixed point set, the other one is completion. Just an idea of what is going on here. Too many letters. The whole point is you get a manifold, take a group, and then you just go at the fixed point sets of the whole group, whatever there is, manifold, and you take the normal bundle, and the normal bundle, since the normal, well, the group is acting on the normal bundle, and then you simply go and classify whatever you get after this fixed point data. So you see, you take your manifold, and then you take the normal bundle on the fixed point set, and then you take this pair, and this pair lives in the relative bordism groups on which you allow any subgroup in the interior, but as isotropy, but not all, only almost all on the boundary, because now you go to fixed points, so they are not on the boundary. And when you do this was done by Tom Dick. No, these relative bordism groups are nicely organized by bordism groups of Kraus-Magnus. So the UN, so the use in this case because it's the stable case, and that's somehow easy to understand because they give you some formal. They give you some generators, equivariant Conner-Floyd Chern classes and whatnot. So what I'm putting here is that you may also localize on the Euler classes of this representation without fixed points of the whole group, and then one can show that this ring becomes This ring on the right. These are the Euler classes that we saw. Then there are the inverse of them that are positive degree. And these Y's that are here are this projective space. And when you take a representation, you add it with the trivial representation, take the projective space, and the whole point is to get, when you get the fixed points, is to get precisely projective bundle with normal bundle is the representation. So that you can precisely get these resonances that you want. So then this map here on the left, this map is what is important that is injected for the circle. More than for G compatibility. No, this is not true what I just put here, but this is for a circle or the cyclic group C sub P, not G compatibility. For the circle of G, for there are more fixed points that you have a different. But if it's injective, then we can use it. The other one is completion on a specific idea. So you take your manifold with a G action and you forget the action, whatever it is. You forget the action and then you get the idea. And then you make complete on this idea. And with a specific map that was called by Tom Dick bundling transformation or bundling transformation, you may go to from the bordism, equivariant ring to the bordism groups of the classifying space. And then one knows that this bordism ring is this ring of formal series, wherever these classes here are called the Conner-Floyd Chern class, or somehow the Chern class is coming from this classifying space. The point nice here is that Loeffler, who was a student of Tom Dick, Bernhard told me here, in the 70s showed this map is injective also. So whenever there's a tori, this map is injective. The other also map is also injective. And these two somehow maps allow one to somehow detect what's in here by looking what do you do in there. So this is Bernhard, what you meant by Tom Dick square. That you put
this integrality, and so this is from his, I think, his paper about integrality theorems.
I think so, yes.
In equivariant bordism. So that's a fantastic paper, and there he writes down such squares. Good. Says, okay, if you have a homotopy theoretic equivariant bordism class, which satisfies some what he calls integrality, namely that it lies. Okay, so
it lies in the image of some specific manifold.
Right. So then it's okay.
So then here we have on the horizontal lines the localization on top, on the completion on the bottom here, and then one can somehow bring the Euler classes that are on the top to the bottom and take them as the classes you want to use to invert on the bottom right. So this diagram is the one that is being used. So in the Igor showed that this is for the case of ZP, and again, I may say things that need to be updated. So Igor showed several things in this square whenever there was the cyclic group Z mod P. That is a perfect square, showed on pullback of abelian groups, and it's a pullback of rings. A lot of structures. So with this, a lot of structure one can. Not me, Igor can get the information from here out of here. Yeah, I'm not going to claim I did it.
Yeah, so that's actually also how Jack got the geometric one. It's a similar square for the geometric one, and the upper right corner is replaced by something smaller.
Yeah, exactly. You need to somehow control the representation.
Yeah, you sort of have to like take the inverse of the series. I guess.
So the Euler classes, they are not allowed anymore, as you
Exactly.
explained on the background. So just the negative.
You just leave the negatives and
yeah.
But you also have to change basis somehow, like so that instead of the series, you have kind of this inverse.
Yeah, you need to put the exactly. You need to do some job on the bottom. Look, this is what this is. But now I'm using now Hanke's result. So we were doing everything homotopically, and you can see on the first line I'm doing geometrically. So on the vertical map here is the Tom contracting map. And what Bernhard showed is when the group is a toral, more general, but In particular, he showed this important thing, that this map from the geometrical bordism group to the homotopical bordism group is injective for the total. She showed many more things, but
Maybe
among,
it was not before.
it was,
So it's the square which
this was not before, this one, the geometrical one. I didn't locate it in the literature, but doesn't matter.
Yeah.
It's injective. So this, you know where I did maybe Buchstaben and Ray claims that you did, but maybe I'm wrong. So then Löffler already in the 17th and the Buchstaben and Ray also used it. They defined something that is called the universal toric genus. Namely, you go to the geometrical bordism groups, and then you just somehow compose with the bonding transformation of something, and then to the completion map. And then you end up in this formal series ring. And there is a somehow very geometrical way to see what you get from the left-hand side to the right-hand side. And the way to do it, which was done by Conor Floyd originally, and then somehow used it several times, is to do this very somehow nice idea, which is you take the three-dimensional sphere with this action of the circle, and then you construct this manifold which has 2 dimensions more, and somehow is precisely somehow encoding the way that you can multiply by these order classes. So when you have these manifolds, they also become not only it's a manifold, they become you can endow it with an action of tk, which is given here. And in this way, we can perform this procedure recursively. And the point is that the image of the manifold on this map becomes all these things. What is nice is that these are now manifolds living in the bordism ring. In particular, if you want this to be 0 here, you better have all these ones 0 here, but these ones, you know that they are 0 if the Chern numbers of them are 0. So then you manage to make a problem that is equivariant, in some sense non-equivariant anymore, and then you can just use your usual tools of the bordism ring, among others. But there's this universal toric genus map, I think, but I don't know, so that if you plug the constructions that you were doing yesterday, because they're elliptic, and then you have 2 circle actions, and you plug in here and you put it in here, and you just calculate what you get, you should get something similar as you were showing yesterday, specifically because your action has fixed points, and then they will show up here with a specific. This is a universal genus in the sense that a genus is a map from the bordism ring to some ring, whatever that is a genus, and so in this sense, this is the universal toric genus in that sense. But anything that somehow comes from here out, you may factor it to this one because it's injected. Good. So this was used heavily by Buchstaber, Ray, and Panos. They wrote a nice book on toric manifolds because, well, not because, I don't know. But one motivation is somehow to construct specific generators on the bordism ring and in all these classes that are toric manifolds, not toric varieties, toric manifolds, because they have a very nice way to construct certain manifolds with the appropriate somehow structure. So what I think is the result that is very nice on Sinha's paper is this result here, which is that one can take an abelian group, multiply by the order class of representation, and then restrict the bordism group to the kernel of the representation, namely the subgroup of elements which somehow fix the whole vector space, and that this is exact. So when I saw this, I thought this must be a mistake. And how can this be exact? Because I was always thinking geometrically, and geometrically is not exact. So you put geometric maps here, and it's somehow geometrically easy to see that it's not exact, but somehow this might give some ideas of what happens in the stabilization process. And if you would just take the bordism, let me put 2, and then I go to the C3 and 2. You might take the torus that was drawn yesterday by young. What's your name? Okay, I cannot say. Anyway, so you put the C3 action on this, on the tori, and so this tori is easy to see that doesn't come from any class from the left. Just by simply noting that you have a two manifold with a circle action and you see how many fixed points there are, you get it hidden, and then there are three fixed points on the other side. So, but curiously, you just stabilize this picture, and then suddenly this one has a somewhere in the left, which I don't know how to think about it, and I don't know where does it somehow, where does it appear the one on the left that has it? That somehow it troubles me head all the time because I don't know how to think these things homotopically. Nevertheless, homotopically it is exact. Namely, then the idea of Dev is, since we know that these objects are free as mu modules, then let's get some sections. But these sections, these sections may allow us to construct some classes. That is a generalization of these gamma classes that appear in the universal toric genus. These classes are simply, well, take an element in the bordism ring, restrict it to your subgroup, and then use the section, bring it back, and since now it's on somehow maps to 0, then it has to come from a multiplication of another class. And this you can just perform it as a machine. Of course, the problem relies on this section that we have at the moment that we have no control of the section. There is a section, but we don't know exactly what happens with the section. And the point is that unless the representation that we're using is just the standard one, giving just one turn around of the circle or going backwards once, there is no control of this somehow section. When the action just gives one turn, you just simply take the manifold with a trivial action and you don't do anything else. But if you have some subgroup here, some K group, some group here in the kernel that is non-trivial, then it's not clear how to do these sections. But now that we know, well, I don't know, but somebody knows exactly what is this bordism ring, perhaps one can exactly know how to hook up these sections in a very intelligent way. So the point is that Dev at some point assumed, incorrectly said that this was a ring homomorphism, this section, and it turned out not to be. And moreover, that one cannot control very much what's going on. So this is an example of his. I don't know if Bernhard, it was given this example to him. But let's just do this specific construction. Let's just take any class with a circle action restricted to the C mod 7. And then let's just take this class, this Euler class, divided, so just multiply by the negative, the inverse of this E4. And it could be represented in the model that I put here, in the model that I put here. Because it's stabilized, I could think of it as a map of the 1 point compactification of this representation to the 1 point compactification of this representation, where the map Z goes to Z squared. But somehow this class lands on the right hand side, and as we said, well, you can lift it because there's a lift. Where do you lift? You could also you could try to lift it where it should not be left, because you should lift it to some class that is represented. That is a class, and the class that one should be lifting to, or there are many, no, is this one here. This is a class on which you just, I don't know if you see the point, because we want to lift it to an integral class or to a circle class. We need to add 7 to these things so we can perform this C to C squared. So we're sending it not to the same one, but to another one, and this. If you take another one, it's just what we learn in what we're teaching in the university, about C mod P congruences. You need to use the properties of the field F sub P, and therefore it's not so clear how do you construct these sections in an intelligent way. Maybe there is, but if you start doing it like that, there is no clear control of what's going on and how does it multiply and what happens later. So this difficulty is what somehow derailed the proof of of Dev, but just as a geometrical interview, these classes that I'm talking about are precisely these geometrical constructions that I showed before in the universal Turing games. It's exactly that. So that's algebraic, this is geometric. And whenever we have such a representation that is raw, exactly what we're doing is precisely constructing this manifold in the manifold sense. Before it's algebra, here is in the manifold sense. But with this representation, we don't know exactly what it is if I change the representation. I don't know what is the appropriate manifold that goes there. And so instead of saying that the theorem is false, but he took the proof of the theorem is wrong, but the theorem is correct. And this is mine, this is not Dev. Maybe the conjecture is that is correct. It's just one has to somehow fix it. That's what Dev somehow would like. That you can generate with these specific relations and these specific classes, you can generate a whole equivariant bordism ring. And what somehow he envisioned is that these specific gammas may have a better role in the description of these equivariant bordism rings. And they're very geometrical, these gamma functions. And so he wanted somehow to share these no, because I need to go back to his wording. So this is what so I'm just somehow contextualizing whatever he wrote here. So these are the classes that I was just mentioning. I represents the winding number of the representation, and so then he puts these different questions. Is there a way to fix the problem? Is there a way to somehow choose appropriately the lifts? The lifts means you have it. Yeah. Good. So then I have to then it's done. In order to somehow understand exactly how to do, but I need to read it then for. Again, this is not my talk. I'm talking on Dev's behalf. Then he has also this question, which is he wanted. It would be nice to know what is the image of just this subring on the geometric bordism ring, exactly that one, or more. The question is. Do I know what are the generators of manifolds with isolated fixed points? What are the generators? Are all of them projective spaces with linear actions, as we were learning from the algebraic geometers, or not? He might claim, yes, he has a proof that whenever you have three fixed points on a four-dimensional manifold, then it has to be coordinate to the projective space of a specific representation. So he was thinking, if this is a generic statement, that the projective spaces of this linear representation are the generators of the bordism ring with isolated fixed points. Then this question perhaps already solved by Paul, which is, can we define these gamma v's without use of this freeness result? I don't know, maybe the function, these gammas, without using, or basically in an explicit way. Can I define it explicitly, these sections? Or these gamma functions. This question here on formal group laws, I must admit that I didn't get it quite well, so I leave you to read it. And finally, again, some integrality conditions about the image on the fixed point data that were used by Tom Dick to somehow say when a class is coming. When the information of the fixed point data somehow tells me what is the manifold behind. This I think was already done by Tom Dick in K theory at the time. I don't know what he meant by this class. Now I know this talk was awkward, and I knew it was going to be like this. Nevertheless, I thought it was good to listen to Dev and to that he told me his thoughts, that he's not going through a good time in his life. So I was listening and I put, and I'm sure he's happy that we did this, because he wanted to specifically say that he had a mistake, and that the mistake is there in this paper and it hasn't been corrected. Bernhard was telling me he should correct it, but sometimes people have problems or whatever, and then forget, and then it's still there, the problem. But so one way to correct it is to tell the community there is this problem in the paper, and maybe someday it will be correct. As I was telling Bernhard, maybe he doesn't do it because one wants to correct the mistake, not just to say that there's a mistake. And he's wanting to correct things. That's why he's putting all these questions. Please correct the mistake. Please correct the mistake. But nobody has correct up. Maybe. So thank you for listening, and thank you for listening, Dev. I'll tell him that you were all amazed by my talk. My dev's talk. And he will see it in Zoom, so that's why you were embarrassing.
Bernard, it's great that you accepted to do this. So it's it was a great service.
Oh, thank you. I didn't read the whole days then.
But just the point, why do you want to avoid using of the Gustavo's, the use of Gustavo's theorem?
Which theorem?
Comenzane?
No, well, because no. When he said no, what he meant is because it's just a free module, then there is a section, but one needs to use a little bit more, like a more geometrical thing. But if Paul somehow has it, but somehow it's very simple, just because it's free, there's a section. But no, it has to be some more interesting thing, because like that, it's not working. That's what he meant. Somehow, and geometrically, what is that you're doing here? Well, anyway, thank you very much.